Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to build off of some of the things we have already learned in terms of when a acid-base system is in equilibrium, which way does it favor, and also on net reactions. So in redox chemistry, we did net redox reactions, and today we're going to look at doing net acid-base reactions. But before we start that, we're going to do a quick review of favorability, which essentially allows us to understand whether a K value is going to be greater than 1 or less than 1 when an acid and base react. So the first thing that you need to be able to do is identify your acid and base on the reactant side of the reaction. And then you will have to use the information below here as well as your data table to figure out what side is going to be favored. Now, the majority of the time, the products are going to be favored. There's really only one scenario in which the reactants are going to be favored. So let's start with the two of the easiest scenarios. So if I have a strong acid like hydronium, now for us in a net reaction, all strong acids are actually going to be written as hydronium. So whether it's HCl, HClO4, or HNO3, etc., really as a net reaction, what these things are H3O+. So we would always write them as H3O+. If any strong acid reacts with any weak base, and I'm going to use A-, which would be a weak monoprotic base as my example, these reactions will always favor the products. Now, I'm not going to draw an equilibrium arrow in here because the majority of the time this is a quantitative reaction where essentially 99.9% of the reactants become products. Now remember, this hydronium would donate an H to the A-, and so it would become H2O liquid, which would be its conjugate base, and A- would become HA, which is its conjugate acid. So I do want to say this, very rarely this will be in equilibrium and favor the products. The majority of the time, this is going to be quantitative. At this level of chemistry, we don't need to know when this happens, when it's in equilibrium and favors the products. We only need to know whether it favors the products or reactants, which is that black arrow. So I'm going to say this one more time. Sometimes when a strong acid reacts with a weak base, the system will be in equilibrium and favor the products. And most of the time, when I have a strong acid reacting with a weak base, it will essentially go 99.9% forward. We call that quantitative. When you move further on in chemistry, you will learn when the equilibrium happens and doesn't happen. But at this level, all we really assume is that it quantitatively goes forward. Okay, the other one that is very easy to figure out is if I have a strong base, and remember strong bases are usually a group 1 metal cation with hydroxide. So when it dissociates, the ion that actually matters is just the hydroxide. It's the strong base. Reacts with any weak acid. This, again, majority of the time is quantitative, 100% forward. There are a few times, a few weak acids where this is in equilibrium, but it's very rare. All we really care about is that it favors the products. So remember that the weak acid would donate its hydrogen. This would form water, and we would be left with the conjugate acid, A-. So far, out of 4 scenarios, 2 are going to be favoring the products. So if you have a strong acid or a strong base as a reactant, reacting with any weak acid or any weak base, it will always favor the product side. The K will always be greater than 1. but on a few rare occasions, this will actually be in equilibrium and favor the products. We do not need to know when it is in equilibrium anymore. It used to be part of the curriculum, but no longer. Now, the other thing I want to point out here, everybody, is these K values here. I have not written Ka or Kb. And the reason for that is these are not Kas and Kbs. A Ka is when an acid reacts with water. A Kb is when a base reacts with water. These are acid-base reactions where both reactants are not water. So this is strictly a K value. It's not an ionization value of Ka or Kb, which is an acid reacting in water or a base reacting in water. All right, we have two scenarios left. The third one is I have a weak base like A minus, and it's reacting with a weak acid HA. These will always be in equilibrium, always. And I have a fourth scenario, same idea, a weak base, A minus, and it's reacting with HA. This will always be in equilibrium, but some of the time it's going to favor the products, and some of the time it's going to favor the reactants. Now, when it's going to favor the products is if the acid is above the base on our acid-base table, it will favor the products. And this will have a K value greater than 1. In our last scenario, if our base is above the acid on the table, it will favor the reactants. So if the base is above the acid on the table, it is going to favor the reactants. And the K value is going to be less than 1. So again, if HA is above A minus, we favor the products, the K is greater than 1. If the A minus is above the HA, we favor the reactants. So let's have a look at this example here between ammonium ions and HS minus. And what I would do first is I would identify these things as either an acid, a base, both, neither. Now I'm going to go to our table in a moment, but I'm going to tell you that ammonium ion here is an acid only. Therefore, this has to be acting like an acid. And when I compare it to its partner, which its conjugate is, if you look here, I can tell that when it's moved from NH4 plus to NH3, it has lost an H plus, which essentially means it donated the H plus, so it has to be the acid, and this is the conjugate base. Now, HS minus is actually amphiprotic. It could be an acid, it could be a base. It has a hydrogen to donate, it has a negative to accept. However, it has to act as the base because the NH4 plus can only be an acid. When I compare it to its partner, I can see that it has accepted an H plus because it has one more hydrogen and one less negative charge. So this is now a conjugate acid. And of course it has to be an acid because that's the only thing H2S can be. So this is the conjugate acid. So now what I'm doing is I'm just focusing on my reactants. I need to find them in their table and I need to see how they are orientated relative to one another in the table. So here I am at my acid-base table, and I've located my acid on the table down here. And I've also located my base, which is HS minus up here. So based on what I told you, the acid is below the base, HA is below A minus, and so we're going to be in equilibrium, but we favor the reactants. Now let me explain to you why scientifically. Why would it favor the reactants? NH4 plus is an extremely weak acid. It's almost sad to call it an acid. If you look at its Ka value, It's 10 to the negative 10. At this point, we almost say it doesn't react with water. So it really doesn't want to give up its hydrogen. HS minus is a fairly strong weak base, but it isn't super strong. And so it wants to take a hydrogen, but it's not crazy about it. And if this thing, NH4 plus, really doesn't want to give it up, and this isn't really, really strong to take it, then it's not really going to exchange a proton very often. Well, if it doesn't exchange a proton very often, then you're going to have more reactants than products, and therefore the reaction is going to favor the reactants. Now, this isn't a question that we have in our booklet, but I thought I would just kind of mention the other possibility. So let's imagine we had carbonic acid, and I mix that with HS minus. Because the acid is above the base, this reaction would be in equilibrium, but it would favor the products. H2CO3 is fairly good at giving a proton. HS minus is okay at taking it. This would probably favor the products, but very little, as the difference in height between the two is very small. So this would favor the products, but probably not a lot. Whereas if I say had HS minus reacting with something like this, which is higher up the table, this would also favor the products, but you would actually have more products than if you were reacting it with H2CO3. This is very similar to redox chemistry. The bigger difference in height on the table between an oxidizing agent and a reducing agent, the faster the reaction, the more violent it is, the more energy exchanged quickly. Same thing here. The bigger difference in height between an acid and base is going to cause the reaction to favor more to the product side or reactant side. So for instance, if HS minus was reacting with HPO4 2 minus, this would favor the reactants even more than our first reaction with NH4 plus. Next, we're going to look at writing net acid-base reactions. So there will be no more double replacement reactions like earlier grades. We would never write sodium hydroxide plus hydrochloric acid is making water plus salt anymore. We have spectator ions in there, like the sodium ion and the chloride ion, and so those would not be included in the reaction. This would actually become H plus and OH minus. So we need to learn the rules of how we write these reactions without spectators. And so in the box below, we have these rules. The first thing we would do is we would read the statement and we would identify all of the substances as acids or bases, and even both, because some are going to be amphiprotic, or neutral. So this is, again, very similar to redox, where we would identify something as an OA, RA, both, or neither, except here we're identifying them as an acid, base, both, or neither. Now, what we have to be very careful of is when we are dealing with strong and weak acids. Strong acids simply become H3O plus and their conjugate base. So HCl is H3O plus and Cl minus. Hydrogen iodide, hydroiodic acid is going to be I minus, hydrobromic acid Br minus, chloric acid ClO4 minus, and so on, nitric acid, sulfuric acid. So we got to change all strong acids essentially into hydronium. Weak acids stay as is. So if I had hydrofluoric acid, I would write it as hydrofluoric acid. I would not change it into hydronium and F minus, because the majority of the species involved is HF, because HF, when it ionizes in water, does it less than 50%, and so we have more HF than we have hydronium. The same thing is true of, say, vinegar. It's a weak acid. I would write it as vinegar. So to clarify, whenever you have a strong acid, you simply write it as hydronium, and you can include its conjugate base anion. However, all of these are going to be neutral with the exception of HSO4-, and therefore they will not react. Then what I would do is I'd find my strongest acid on my list, I'd find my strongest base on the list, and then I would react the two, exchanging a proton from the strong acid to the strong base. And then I identify the favorability, which we did in the first part of this lesson. This sounds, again, very similar to redox. So redox would be a species list, identify everything as an OA, RA, both or neither, find the strongest OA, find the strongest RA, exchange electrons, and we're done. Here it's the same. Species list, strongest acid, strongest base, react the strongest acid with the strongest base. Everything else is a spectator, and I don't worry about it. Okay. All right, ionic compounds, of course, that are soluble will split into two ions. So let's start with this first question. A solution of sodium cyanide is mixed with hydrochloric acid. So in my species list, I would have water because there's a solution. And then it says sodium cyanide. Sodium is soluble with absolutely everything. So aqueous, cyanide, Cn- aqueous. And then I have hydrochloric acid. Now hydrochloric acid is a strong acid. So I need to write it as H3O plus aqueous. And then its conjugate base Cl-. Okay, so there's step one. Step two, I need to figure out what's an acid, a base, both, or neither. Now, water is amphiprotic. It could be an acid or a base, but I don't even consider water as part of the reaction unless I have no other acid or base. So for instance, if I had a species list and I had water and then I had something that was neutral, and then something that was a base, then water would have to act as the acid because it's the only acid there. But if there is literally any other acid or any other base, it is going to be a stronger acid or base than water because water is the weakest acid and it is the weakest base. Sodium ions is a group 1 ion. It's neutral. Cyanide ion is an anion and it is a base. H3O plus is strong acid and Cl- is the conjugate of a strong acid, so it is neutral. I then identify my strongest acid and my strongest base. Well, strong acid has to be my strongest acid. There's no doubt about that. I then only have two bases to work with. I've got water and cyanide ion. Water I would only choose as my base if I literally didn't have any other choice, but I do. Cyanide is a stronger base than water. I then would react the two species. So I would have hydronium ion aqueous plus cyanide ion aqueous. And I'm just going to draw a rectangle here. We're going to insert the type of arrow that belongs. I would have my acid donate a proton to my base. So what's left of hydronium would be water. And the Cn- has gained an H. And it has gained a positive, so now it's not positive. So there's my two pairs. So I've got a conjugate pair of hydronium and water. That's one conjugate pair. And I have Cn- and HCN. That's another conjugate pair. The last thing I have to do is identify whether this is in equilibrium and favors the products, in equilibrium favor the reactants, or if I just have a quantitative reaction. Now, whenever I have a strong acid with any base, I'm just assuming that it's quantitative, and so this would go 100% forward. Now, the idea of is this quantitative or not is not tested on the diploma, just the favorability. So does it favor the products or does it favor the reactants? What I'd like you to do now is pause the video and try to answer question number 2 by making a species list and following the set of rules. So now that you had a chance to try it, let's go through the answer. Starting with our species list, it says a solution. So I have water of potassium phosphate. Potassium's a group 1 metal cation and very soluble. So phosphate is PO4 3-. It is mixed with a solution of sodium hydrogen sulfate. Now, hydrogen sulfate is one polyatomic ion. It is not two different ions, so it's HSO4 minus aqueous. So let's label this. We have a water which can be both acid or base. This is a neutral. We have a base with phosphate, neutral sodium, and HSO4 could be an acid, or it could be, well, no, it can't really act as a base because it's the conjugate of a strong acid. So theoretically, you can say it's a base, but it would never act as a base because HSO4 minus is the conjugate of a strong acid. So I'm not even going to look at my table at this point. Other than water, I only have one available base, phosphate, and I only have one available acid, hydrogen sulfate. So what I need to do is I need to react those two. HSO4 minus aqueous is going to react with PO4 3 minus. Again, HSO4 must act as the acid. PO4 3 minus can only act as a base. I'm going to draw a rectangle, and then I'm going to show the hydrogen being donated from the acid to the base. So what's left of HSO4 minus is SO4 2 minus, aqueous. And if PO4 3 minus gains an H, it becomes HPO4. But it has to have one less negative because the proton is one positive, 2 minus. Now, if I was to look at my acid and base table, HSO4 minus is a very, very strong, weak acid. It's very high up the table. And phosphate is the strongest of the weak bases. It's very low down on the table on the base side. So I would say this is in equilibrium, but it does favor the products. Pause the video now and try the next two questions. In question 3, we have perchloric acid, which is a strong acid. So that would be H3O plus aqueous and ClO4 minus aqueous. Of course, there has to be water there because it's an acid. It's dissolved in water. And then it's reacting with ammonium hydroxide. So ammonium ion and hydroxide ion. And don't have to write water again because we already have it as part of our list. So going through, hydronium is an acid. Perchlorate is going to be neutral. Water could be an acid or could be a base. Ammonium ion is a very, very weak acid. And hydroxide is a very strong base. It is strong base. So I don't think there's a need to look up what's the strongest acid or strongest base because we have a strong acid and we have strong base. So we're going to react those two. This would be a 100% quantitative forward reaction. So this would have a single arrow going forward. And then I can say that it makes two waters, or I can write H2O plus H2O. For question number 4, it looks like we have another strong base. So lithium hydroxide is a group 1 metal cation, lithium ion, which is 100% soluble with hydroxide. So I have strong base. Of course, there's going to be water there. And because this is in a solution, there's got to be water. And this is reacting with hydrofluoric acid. Now, this is where most students make a mistake. They would write hydrofluoric acid as H3O plus, comma, F minus. But that is not the case. Hydrofluoric is a weak acid. It ionizes in water less than 100% and less than 50%, which means I have more HF than I have hydronium. And this species list is a major species list. The major species in solution here is HF. So the next thing I do is identify everything. Lithium would be neutral. Hydroxide is a base. It's strong base. This could be an acid or it could be the base. And HF is an acid. Now again, other than water, I only have one base and I only have one other acid. Water would only be the strongest acid or base if I never had any other option. So I now know that hydroxide is going to be my strongest base and HF is going to be my strongest acid. I'll start with HF. It's going to donate its hydrogen to hydroxide, like so. HF would turn into its conjugate base, F minus, and hydroxide would of course turn into water. Now, I don't know if this is in equilibrium and favors the products, but I definitely know that it favors the products because hydroxide ion as a reactant is always going to have a K value greater than 1 if it is reacting with any weak acid. It could be in equilibrium, but that's beyond the scope of our course at this point. What I'd like you to do now is pause the video and try questions 5 and 6. In question number 5, we have a couple of ionic compounds being mixed together in solution. So starting on my left-hand side here, it says a solution of sodium hydrogen carbonate. Now remember, hydrogen carbonate is one ion. It's a polyatomic ion. So I have sodium ion aqueous, and then hydrogen carbonate ion aqueous. This, of course, is in solution, so water is present. And it's reacting with ammonium chloride. I'm not going to add another water because it's already part of my list. I know it's in solution. So then I label everything as acid, base, both or neither. So sodium is neutral, so neither. Hydrogen carbonate could act as an acid, or it could act as a base because it is amphiprotic. It has a hydrogen and it has a negative. Water is amphiprotic, but it's the weakest acid and weakest base. Ammonium ion can only act as an acid. And chloride ion is neutral. So when I look through here and I check my table, I find that ammonium ion is the strongest available acid and hydrogen carbonate is the strongest available base. So what I need to do is react those two. So NH4 plus aqueous will react with HCO3 minus aqueous. And again, I know that NH4 plus has to be the acid because I don't have any other strong base that's strong enough to react with it other than water. So this is going to be in equilibrium for sure. The ammonium ion is going to donate a hydrogen and it's going to turn into ammonium molecule. And H2CO3 is going to, or sorry, HCO3 minus is going to turn into H2CO3 aqueous. Now, when I look on my table, HCO3 minus as a base is higher up the table than NH4 plus. Therefore, this reaction is in equilibrium, but it is going to favor the reactant side. Okay, let's look at our last one. A solution of sodium chloride. So sodium ions aqueous, chloride ions aqueous, that's salt water, is mixed with a solution of potassium sulfite. So I have water there, potassium ion, and sulfite ion, which is SO3 2 minus aqueous. So let's label all of these things as acid, base, both, neither. So I've got neutral sodium, neutral chloride. Water could act as an acid, it could act as a base. Potassium is neutral, and sulfite is actually a fairly strong base. So I only have two bases to choose from. So I have SO3 2 minus and water. If I have any other base other than water, it has to be the strongest available base. And then I only have one acid, which is water. That is the only acid available to me. So this is actually an ionization. This isn't a classic acid-base reaction. This is sulfite ion reacting with water to produce hydroxide. This is a Kb. So starting with my acid, H2O liquid, reacting with SO3 2 minus aqueous, I know all Kb values are less than 1, and so I know this is going to favor the reactant side. Also, my base is above the acid on the table. The acid, which is water, will donate its proton to the sulfite, end up turning into hydroxide ion, aqueous, and then HSO3 minus aqueous. So this last one is actually an example of Kb, which we've already spent some time on. So what I'd like to do is just zoom out and show you this entire page and how we've essentially covered all of our possible scenarios other than a Ka. So in our first question, we have a strong acid reacting with a weak base. It's going to favor the products. In our second question, we have a weak acid reacting with a weak base, where the weak acid is above the weak base, and therefore it favors the products. In our third scenario, we have a strong, which is a quantitative reaction, 100% forward. In our fourth reaction, we have a strong base with a weak acid. Again, this is going to favor the products. Whenever I have a strong acid or strong base on the reactant side, it always favors the products. In our fifth question, we have another weak acid reacting with a weak base. However, this time the base is above the acid and therefore it favors the reactants. And in our sixth question, it's really not a traditional acid-base reaction, but rather a base ionizing in water, a Kb. And we know that all Kbs have a value of less than 1 if we're dealing with a weak base. The only other scenario not covered on this page would be a Ka, where a weak acid reacts with water, and again, that would favor the reactants in equilibrium. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.